Welcome to Electronline. In this chapter, chapter 7, we're going to talk about inductors. Now, inductors are actually very simple devices, although there are a lot of different uses for inductors and a lot of different properties about electricity and magnetism that involve inductors. So, what is an inductor? Well, in very simple terms, an inductor simply is a wire wrapped around the tube. That's all it is, a wire wrapped around the tube. So what's so special then about an inductor? Well, it turns out that it has a very special property. An inductor opposes a change in current. In other words, if there's DC current, steady state current, inductor does absolutely nothing. It just sits there and there's no effect on the circuit whatsoever. The moment the current tries to change, that's when an inductor, basically jumps into action and tries to oppose that change. If the current tries to increase, the inductor tries to keep it from increasing. If the current tries to decrease, the inductor tries to keep it from decreasing. And that's why inductors are so useful in electrical circuits, because of that specific property. Now, physically, an inductor, here's a drawing of an inductor, simply is a tube. That tube could be simply a hollow tube with air inside, then it's an air core inductor as we call it, or it could have a metal, or it could have some sort of inductor inside, but typically they like to use metal to enhance the magnetic field through the tube, and we'll talk about that later. But it's simply a wire wrapped around the tube. The tube has a cross-sectional area, it has a length, and also an inductor has a number of turns as we call it. Each loop of wire around the tube is called a turn. It's simply a loop. Also, what you need to know about inductors is the number of turns per length. In other words, if this is a 5 centimeter inductor and there's 100 turns, that means there's 100 turns per 5 centimeters, or 20 turns per centimeter, or 2,000 turns per meter, however you want to express it. Also, when we talk about inductors, we talk about what we call permeability. As we will see later, there's always a magnetic field around the wire that carries a current, and therefore, as we loop a wire around an inductor, there'll be a magnetic field inside the tube or inside the core. And the permeability is the amount of magnetic field, or I should say the permeability is the ability of the magnetic field to exist inside that tube relative to what's there. If it's simply air, then we use this permeability, which has the units of 4 pi times 10 to the minus 7 Webers per amp times meters, or Teslas times meters per amp, depending upon what units you want to use. The permeability becomes larger as you put, for example, metal in there, because metal can basically allow more magnetic field to exist inside the tube versus air. And so we'll show you the difference about that later as well. The key idea with an inductor, this is the electrical symbol for inductors. It looks like a little wire inside a light bulb, the old incandescent light bulbs that is. And you can see that if the current is constant, either if the current is zero or the current is not zero but constant, doesn't change, the voltage across an inductor will be equal to zero. However, if the current is increasing in this direction, the current is flowing in this direction, the current is increasing, the voltage across the inductor will be some value, and it will be negative on this side and positive on this side. In other words, it will set up a potential difference across the inductor that tries to oppose the increase, that tries to drive a current in the opposite direction. If the current is decreasing, then the voltage across the inductor will be like this, positive on this side, negative on this side, because it will set up a current in the same direction as the decreasing current, trying to keep it from decreasing. So that's how we look at inductors. There's only potential difference across an inductor if the current is actually changing. Here's the equation that defines how much the voltage is across an inductor. It's equal to the inductance, L, the inductance of the inductor, times the rate of change of the current through the inductor. Now, what do we mean by inductance? Well, let's go over here for a moment and take a look at this. A resistor has resistance, and we use the letter R to indicate resistance. It opposes a current, a DC current, AC current, doesn't matter. It simply opposes a current according to Ohm's law. A capacitor has capacitance. It has the capacity to load up charges, to store charges. An inductor has inductance, and we use the letter L for that. And the units for inductance is henries. Now again, what is inductance? Inductance is the ability to oppose the change in the current. The larger inductance, the more it can oppose the change in the current. The smaller inductance, the less ability it has to oppose the change in the current. And the inductance can be found by, and I didn't write the equation down, so let me write the equation. L is equal to the number of turns in the inductor times the number of turns per unit length in the inductor times the permeability of the inductor, that would be the permeability of the core of the inductor, times the cross-sectional area. So what we could do is we could write this in two different ways. We could also write this as L is equal to n squared times mu times A divided by the length of the inductor, and that is typically the way you see it in most textbooks, but it could also be written as follows. You can also say that the inductor is equal to the number of loops times the number of loops per unit length times mu times A. So you could also write it like this, again, where the small n simply means the number of loops per unit length. But this is typically the way you see it in most textbooks. In other words, you can actually calculate the value of the inductance of an inductor if you know how many loops there are. Let's say there's 100 loops or 1,000 loops. You need to know the permeability. It'll be this if it's air. It'll be a larger number if it's a metal core. The cross-sectional area, so the physical size of the inductor is important, and the length of the inductor is important as well. This will give you the size of the inductance. Then you use that number in here, multiply times the rate of change of the current with respect to time, and that will give you the voltage across the inductor. Remember, the inductors typically only have voltage across them, not just typically, but always have voltage across them if there's a change in current, and the voltage will be zero if there's no change in current. Now, of course, one more thing perhaps. In essence, and we'll talk about that later, since the inductor is made out of wire, and since all wires have a small amount of resistance, in essence, all inductors have a small amount of resistance as well. But we'll talk about that later. I just didn't want to forget that, so that you realize that there'll be a little bit of a voltage across an inductor, any inductor, because they're made out of wire, and wires still have a small amount of resistance. But if we ignore that for now, you can think of it like this. So now you know what an inductor is, and we'll do a lot of videos on inductors to show you how we use them, how we add them, subtract them, how we use them in circuits and so forth. And that's what an inductor is.